the percentage uncertainty, right? Which then leads to the value. That's a bit, so it's a two-level question, kind of. So in order to find the uncertainty of the value, we have to first figure out the percentage uncertainty before we can figure out the value uncertainty.
Oh,
So it's a bit tricky. That's why I said these multiple choice questions are not necessarily simple.
is it 0.1 over 40 and
Okay.
divided by 0.05 over 2.5?
Now that's the question. When you have it, so the value is the result of a division. And it can be proven mathematically, but we are not going into that, of course. So we have to kind of remember it. When we have a division, also the result, the data we are interested in is the result of a division. And when we have a division, we actually add the percentage uncertainty. So what we have to do is therefore we have to add the two uncertainties. So we have the uncertainty of the time. So in this case, you said the distance first, which is fine, doesn't matter. And we have, of course, then the 0.05 over 2.5. Of course, always percentage times 100. So we add them up.
Oh.
So, or times 100% to be very, very precise, actually. So that's the key point here. So whenever you multiply, actually it's for the multiplication or division. If the result would be the other way around, for example. So let's say we want to calculate the distance, which is then obviously time times average speed. So it would be a product multiplication. Then, and we're talking about the distance calculated as the measurement of the speed. And this one, then same thing. We would add the relative uncertainty, so that means the percentage uncertainty, add them up, like here, same thing. So as long as it's division or multiplication, which obviously one is just the inverse of the other, we have to add these relative uncertainties, or the percentage uncertainty. And that means, as a first step, and that means we get, for this one, we get 0.1 over 40 is 0.25%. And for the first one, no, the other way around. Why do I say that? Excuse me. The other way around, of course. So 0.25%, 5%, and this one is 2%. So that's the interesting part, right? I mean, it's kind of obvious, but still, this is in terms of value bigger, so to speak. This seems to be like a small value, but because it's in relation to a comparatively small data, 2.5 seconds, that becomes comparatively big deviation or uncertainty, whereas this one, 0.1, although, so everything's relative, we always see that, but it's related to 40, so it's of course only a fraction of what you have here. So in total, of course, as we have to add them up, we get an uncertainty relative-wise of 2.25%. And now, the next step, so that's like step 1. Step 2 is then to say, now, how do I calculate the uncertainty of my average speed? What do I do with this 2.25%, Chris?
Times it with 16.
Yeah, exactly. Okay, yeah. So 16 times this, well, we can either write it like it. Sorry, handwriting. Make it flatter. Okay, that's better. 16 times, well, we can either write it as 2.25% or 2.25 over 100, never mind. And that's then 0.36. Huh? Now, what I have not written here, that's where the significant numbers come into play, right, or figures come into play. Not quite correct. Actually, I get 16.0 if you are really strict.
Oh.
Right. So Hainsworth, what impact does that have on my uncertainty value? Or maybe I write it down here as well. Also, here it's not that relevant, of course, but sometimes it's good for the mental picture. So when I have 16.0, of course I can argue it's 16, but I have 0.36, so I have a dilemma, right? And have to solve it and say, okay, is it now 0.36 or what is my uncertainty value?
0.360?
No, because when you look at this value, that gives you, actually that drives the significant figure for the variation or uncertainty. So if you have 0.0, meaning one digit, then same thing is needed here. So they have to match. So in other words, we cannot talk about a 16.0 meter per second plus minus 0.360, for example, which of course is the same as 36, but just to say, it has to have the same range, meaning digits. And that means the 0.36 has to become, what do you think, Chris? What does it have to become in consequence to match the 0.0?
0.4?
Yeah, exactly. Huh? So there has to be the match between these. This one, I put it in red so to highlight it a bit. Huh? So in consequence, the proper answer is therefore 16.0 plus minus 0.4. So that's the answer we are looking for. And Hainsworth, of course, it's a C, right? So this one. So, I mean, obviously 0.2 doesn't, from a calculation point of view, doesn't even qualify. Same, of course, here. These two are out of question just from the calculation of it. Of course, if we would maybe multiply that, one quarter times, no, it's not even there. Huh? So if that would be 0.5 times 2%, that would be something else. Then we would get 1 eventually. But with this one, no. So the question is therefore, is it C or D, right? So that's the ultimate question, frankly speaking. The moment we realize, okay, division, multiplication, we are adding up the respective contributors, the percentage, then, of course, like you said, we multiply that with the value. Okay, perfect. There we go. It doesn't matter. We go for the 2.25, or theoretically we could as well get 2.257 or whatever, depending on the values. Then we would still take 2.257. So the percentage is not being adjusted, so to speak. We take the full values, which causes sometimes some problems, but of course usually not in the tests. And then it's exactly this question remaining. Huh? So meaning this one. Then we have to realize, the second barrier, so to speak, is to realize, one digit here means one digit there. Hence I have to adjust. Huh? Okay?
Yeah.
All right. Now, question 3. Measurements of the acceleration of the free fall, also for G value. This is precise but not accurate.
D.
Okay, and why?
Because the values are all very close together, so it's precise.
Okay.
But it's
Yep.
not close to the actual 9.81, so it's not accurate.
Exactly, huh? So close to each other, better said here, right? Like you said. Close to each other, but not close to the real value. So not accurate. Okay, good. That was a shorter one. Then number 4. So to reduce the systematic error. That's an interesting question. Some of the answers sound comparatively complicated, right? Not necessarily do we in all cases really know what is meant. Maybe yes, maybe no. That makes it, of course, a bit tricky. So in such cases, it's best just to cut down and say, what is it really all about, that systematic error? So which one comes closest, or in the end, is the real answer?
A.
Okay.
Because
Okay.
A is adjusting apparatus.
Yeah, very good. And what are all the other 3 doing?
They're repeating trials to find the average.
Exactly, very good. So it does not eliminate that at all. Huh? So that's why it's good that you cut through it, right? It sounds complicated. Some guarantee get confused by that and say, "Wow, what is this internodal distance on a standing wave, etc." Right? So, but it's not even important. It's several again, or repeatedly, or a large number. So it's basically 3 different expressions to say the repeated. Yeah, that's good. Now number 5. Basically similar to what we had in 3 a bit.
B.
B, okay. So obviously are they accurate to within 1 millimeter? Nope. They are not. So it's a no. So then therefore we are eliminated already C and D. And why is it now not A?
Because all the values are a millimeter within a range.
Yeah, exactly. Huh? So this one is, just have to really carefully look at it, and the answer is then quite straightforward. Yeah, that's good. So they are not always like that, right? Sometimes is obviously more complicated, like question 2. Then this one is a bit more straightforward. This number 4 seemed complicated, but it was just the wording which revealed the answer actually. Exactly. Now this one is where we have to. Yep, it's a bit similar to 3 in terms of obviously calculation. And then it has some issues, of course, as well. I mean, if you look at the marking, that's not really fair, frankly speaking, because this is rather a complex question. You have to do a lot of work. This one is comparatively simple, right? So this one was already quite something, which only gave 1 mark as well. So I would say if this is at least number 2 was at least a 2-mark question, then I would say this is then maybe a 4-mark question, so to speak, huh? Because of what we have to do and what we have to consider. But enough said. So how do we go ahead here, Chris? So what is the
Um,
oh, I mean, independent now, I mean, you have 4 values, right? So independent of how they are related or brought in connection in order to get modulus, actually, that elasticity one. What are you doing with the values given?
finding the percentage uncertainty.
Yeah, so in that sense, it's straightforward, absolutely correct. Huh? So we basically go by, there's only one challenge then, so we go by 0.0, 0.02, let me change to blue, 2 over 2.043. Huh? Yep, and that was my mistake. It's 1 0. Okay, so here we go. So that's for A, then B, C, D. B, how do we have to calculate that one?
0.02 over 0.54.
0.54, and then the other one just 0.01 over 19.62, and D is then just 0.2 over 5.2. So this one, A, is 0.1%, C is 0.05%, this one is 3.8%. Huh? Well, of course, times 100%. I mean, that's the one we. Why did I not calculate B yet, Chris? What may be the reason that I left that out for the time being? It's when you look at for this, you have to look at the calculation of the formula in an answer.
Because it's already less than D.
No. When you look at the calculation, right, what do you have in the calculation? You have F, okay? Yep.
Squared.
Squared. What does that mean for your uncertainty calculation? Do you remember that?
Is it doubled?
Yeah, exactly. So it goes by the power as a multiplicator, exactly. So that is, yeah, so we say 2 times. So let's make that in red to highlight it a bit. 2 times, exactly. So it goes by the power. Huh? So this one here results in double. Or, of course, if it would be, for whatever, in some cases, like it would maybe even cubed, then of course it would be 3 times, which is rare, clearly, for such physical measurements. It's either linear or exponential, but in a squarish function, usually not in a quadruple. excuse me, cubed one. So, okay, yeah, exactly. And that's why we get for that value actually 7.4%. Of course, you can see it's on purpose because if we would not calculate it with double, we will get 3.7. And of course, clearly, then we would see this one, right, as the one which should be wrong. So the D, so the extension slide, excuse me, is then something where we wrong, we would say it's this one because obviously the diameter goes in double. Huh? Okay, so again, this it's a bit similar. I mean, of course, different in terms of mathematical calculation. When we have this one, then it's adding up. When we have the power, we multiply it with that factor. So there are certain things, once we remember them, they just come automatically. The proof would be a different story, but we don't have to prove it. It's just, we have to apply it. Okay, now, number 7. Of course, and there's one more. So that's a bit unfortunate. That number D is on the next page actually. But should have been, of course, on the same page. But sometimes the page break is a bit so. So what do we have to look at, or what are we looking for in order to get the right answer? We can then still swap back and forth between these A, B, C, and D.
In the first, so at the start, when the current increases, there's a larger angular change, but as the current increases to be a larger value, the angle change is less.
Okay.
So I think it's A.
Okay, yeah, all right. That's a good, solid conclusion, right? So you link it, what is being observed, so to speak, is linked in what you should see on the ammeter accordingly, right? Just to go back to this one, that is, yeah, it's a bit of combination of both. Incorrect, the D one. Huh? Okay, good. Then already go to number 8. Let me see. Yep, it's all on one page. Okay, now we use the length of a pencil. And we have, the student A, B, C, D. And, okay, again, similar question. What is precise but not accurate? This time it's visualized.
B.
Okay.
So it's precise because the values are close, but it's not accurate because it's not on 15.
Okay, and why is it not D?
Because D is both precise and accurate.
Okay. Okay, yep, that's a good answer. Exactly. And so that's, sometimes we place it the other way around. And okay, at least like you can see sometimes, fair enough that all the scales are the same 4 times. Once in a while it even is as such, which is of course not really fair, but that the scale is not necessarily exactly the same. So that is maybe sometimes an additional complication. Or it's maybe not shown in the same range, like 13.8 to 15.4. It may vary. So maybe this one is shown from 14.6 to 15.6. That may look different than, maybe even if the range is the same, excuse me, but not the absolute value. So it's 1.6 in range, but the starting value are different. So it's maybe from 14.6 to 16.2, for example, which at first glance looks, of course, then quite different to the other ones. Hence, it's a bit, have to make sure that we are talking about that we really pay close attention to what is really shown there. Huh? This one is now kind of straightforward, but it won't always be like that. Okay. So there's a thermistor, right? So that's the type of resistor we are looking at. And what does the basic, I mean, it's there, but still, nevertheless, to ask, what does the basic, what can you say about the graph? What is happening? We look at the graph.
Resistance decrease as temperature increase.
Okay, can say that exactly. So the resistance is less when the temperature increases, actually. Or the other way around. Depends. Of course, both is correct. Or you can go from the f of x, so to speak, that you say when the temperature is higher, the resistance is lower. It's of course exactly what you said. It's just slightly more going from the x to y, so to speak. Huh? So, and of course we have some additional pictures on the 2 pages afterwards. And which diagram could represent the temperature scale on the amp meter? So you have something like this, and you have something like that. So obviously, what is the major difference between A, B, and C, D, Chris? Where we have to be a bit careful. Just when you look at it.
Oh, the order is flipped.
Yep, the order is flipped, so we have to be a bit. So we cannot just compare them one on one. That's what I want to say, right? So it's not necessarily always in the same order sequence or scaling. Sometimes even like we discussed before. So when we look at the scaling now, I mean, just let's start on this page and then we can do with the other ones afterwards. Is it rather A or B? What is reflecting the right situation? Or one of them, of course, maybe even the final answer. Nevertheless, you have to cross-check with C and D. But which one is it rather A or B? Or is it A or B?
I don't really understand the question.
Okay. So what we want to figure out is that the basically link the increment in resistance over temperature with what we see here in the measurement. So here we just see the temperature, and of course the point is we have an f of x. So here it looks like f of x is r in function of the temperature, right? But we are interested in the temperature. So we have to reinterpret it a bit of what is happening when. So in other words, when the temperature, like you said, right, when the temperature is high, the resistance is low. And when the temperature is low, the resistance is high. And it's not linear, of course, otherwise, of course, it would be even. So this one is quite steep, right? This one is quite flat, kind of. So in this section, what happens at low temperatures?
The resistance is high, and then
Okay, yep. And will it change? Will it make big changes?
yeah,
Right. So which one is it there for, rather A or B?
um, A.
Right. A, right. Well, because what you can say, for example, is, well, let's take this is 50 degrees, right? So when you look at this one, this section here, actually the temperature, the resistance drop is actually not much. So the temperature change is rather within very narrow bandwidth, so to speak, right? If you have a change in resistance, then it will change. So you have to make it very narrow here. So, or let's say from the 50 onwards, in order to have the change properly shown. Do you know? Do you understand what I say, Chris?
Yeah.
Because here it's quite flat, right? But here it's very steep. That means you have big jumps. So that means a little bit of so resistance change will show, or has to show, a big temperature change actually. Okay, so we say A. Okay, then let's cross-check if there's anything we have to change now in what we say.
Well, because the resistance is decreasing.
Yes, right, exactly. Yeah, good one. So hence no. So that's where the significant difference is between A, B, and C, D, exactly. So that basically we have to start on which side do we have to start? It's pretty obvious, but in the context of the question, it's maybe a bit, like you said, what is the question really all about? Then, once it's clear, then of course it can't be like that, because, yeah, it goes like this. Otherwise, if you go like that, yes, then it would be P or C, C or D, huh? Exactly. All right, so we play again. Well, of course, they're all 1 mark because they look at it as multiple choice questions. But again, this is more difficult because you have to figure out the basic relationship. What does that mean for the direction of the scale? That's basically AB versus CD. And then in detail, what happens where? So in this section, what happens and what happens in this section, and to translate that, so to speak, into their respective scale. Huh? So that's at least 2 marks. Okay, last question from the multiple choice. And probably you have to do some calculations. So basically it combines probably a couple of things. So how do we have to calculate the uncertainty of value W, or that energy, or the work actually? In that context, I would rather say the work. We know that energy and work is ultimately the same, but within some context, sometimes it's more preferable to say work, and sometimes it's more preferable to say energy. I mean, again, it's of course the same, but words sometimes help. And here to think of energy, okay, that's one way to look at it, of course. But when you look at this one, it gives you a bit of an idea of a impact of a force out, which is coming from the constant then through that square of the distance or the extension. And that is a bit more like, well, it's like the force being applied on a certain distance, right? Indirectly. So hence, yeah, would rather talk about the work which has been done in order to get that. That's why, of course, we call it W as well here. Nevertheless, how do we have to calculate now the uncertainty of the work being done by the spring constant and the extension?
2 over, is it just 2 over 100?
Okay. Yep, absolutely. Yep, just straightforward. Actually, that's sometimes the good news. Then I just make it like that. Okay. Then what about the next value? How does it have to be connected with the first?
I think it adds with the first.
Yeah, exactly, because it's a multiplication, right? Yep.
0.002 over 0.05.
0.02 over 0.050. Sorry. Again, handwriting. 0.050. Okay, times 100. Anything I would have to consider when I look at the formula?
It has to be doubled.
Yep, exactly. So comes that on. That's right. This is like a combination of what we had in question 3 and whatever, 6, I think it was. So now it puts it all together, right? We have a multiplication, just the inverse of a division, same thing. In that regards of uncertainty calculation, we add them up percentage-wise. And because it's, again, something squared, so we have to double the value of that. Okay, so when we calculate that, I just cut it short. It's 2% plus 8%, which obviously gives us 10%. And because it's the percentage uncertainty, not the final value, obviously then answer B, right, is henceforth the right answer. Okay. So you see, it's within a certain range. I mean, it plays obviously a lot with the like what we had here. With the, excuse me. That's very clear. Accurate and precise, which is then in certain variations of how the questions are being asked. It's about systematic error, how to avoid that or what is behind that. Then typically some calculations. And then some of those more challenging ones, kind of where we have to link a certain behavior with the instrument of what it shows and what the scale should look like in order to measure it properly. Yeah? So that's more or less the core of it, especially for multiple choice. All right. Then, I would just say, then let's go into some calculations. Or not just multiple choice, but as we've seen, in some cases it's already calculations anyway. Here it's a bit different, of course. We focus especially on the calculations. So, I mean, the first one is, of course, very straightforward. How do I calculate it? I mean, we don't do it, Chris, but it's, I mean, how do I calculate the speed?
Just I think we have to turn so 1.8 times 1.26.
Okay.
And then divided by 0.0051 kilogram.
Yep. So obviously the first one is more like about 0.0051, right? To make sure that we measure it all in the right unit of measurements exactly. And because we talk about uncertainty, but we have dealt at that in the multiple choice, not to include the uncertainty at that stage. We just want to have the value, period. And then in the next stage we talk about uncertainty. Okay, so and obviously the question separates that already anyway. Typically, we would not necessarily separate that. It's probably just ask what is the absolute uncertainty. So you have to realize, okay, first I calculate the value of the speed. Eventually, I have to adjust the unit of measurements, and then go into the real calculation, so to speak, about what is really being asked, which is then, the absolute uncertainty. And how do I calculate that one now?
I think you just add them up.
Okay, yep, because it's multiplication or division, right? So we go that way. So we just calculate them. I just give the values. Yeah. Of course, just to say, how do you calculate it for t? Is there any calculation even?
No.
Okay, yeah, exactly. And just like you said, huh? So we multiply them. So obviously, add them up. 5% plus 1% plus 2%. Okay, and anything I have to consider? So that would give me 8%, obviously. Anything I have to consider when I look at the formula?
Divided by 2?
Okay, it's correct. I would, in that context, rather not divide it. Of course, it's mathematically exactly the same, but just to drive home the message, I would just say multiply it by half. Huh? Why? Because, of course, TL over M is half, right? Power of half. So that is where you can link it very nicely because it's power of half. So power is half, and I have to multiply it with the power. So hence it's half here. No? So you know what I mean, Chris, right?
Yeah.
Right. I mean, of course, divided by half is the same thing, but this one is more, let's say, elegant, where it drives the basic rule, multiply with the power. So you explicitly make it like that then. Whereas if you just say this one divided by half, it's a bit, as I say, it's implicit kind of that you divide it. Whereas in we say we multiply it with the power. Okay. So we get 4%. And what is next then on the agenda?
Times the velocity.
Oh, okay. And that was, let me just put it down, 21. That was 21 meter per second. Exactly. So we just multiply that, of course. So we get velocity times these 4% is 21 times 4%. And we get, well, it doesn't matter, but that gets 0.84 meter second or per second. Okay, so that was basically just instead of given 4 different answers, we just have to calculate it ourselves. So the difference is not so big. Now this one is a bit different now because it goes a bit more into some sketch, graph. But it's more about a qualitative answer, right? We don't have to calculate. So what should we do in order to make it as accurate as possible? What about the heights 1 and 2?
A ruler.
Okay, yep, right, straightforward. Take a ruler, and how do we ensure that the measurement with the ruler is now as accurate as possible?
Measure it multiple times and get the mean.
Okay. What else would you say? When you think of a ruler, what could go wrong when you use the ruler a bit in a wrong way? Or what could be the wrong way to use it?
Maybe you tilt it.
Exactly. Avoid tilt. Yes, exactly. So you need something to avoid the tilting. Yeah. Okay. So you have to say something about that. So something which helps you to make sure it's really leveled, also in the vertical way. Okay, so you may have a spirit level or something like that. What else is, when you use a ruler, what may be something which may go wrong when you look at a ruler? Is zero always starting at the very starting point of the ruler or not?
No.
Quite often, no, right? You have a bit of a additional space. And that, of course, is making it a bit more tricky, especially if you put it on, if you have to measure it from here, right? So,
Yeah.
of course, that's why typically in scientific measurements experiments, you have a ruler which really starts at zero, exactly for that reason, not the one we use just under normal circumstances. Okay, then what about the time?
Well, multiple trials of using the
Yep.
stopwatch, and
Okay.
also I think we could use videotaping to to make it more easier to be more accurate.
Yeah, that's a good idea, actually. Yep, absolutely. So we can really stop it then, even if it's over the mark, then we can see it from the video recorder, so to speak. Yeah, that's good. Okay, so that was more qualitative. Now we go a bit into the calculation part. And we haven't dealt with that one before, kind of, but that doesn't make it more complicated. To the contrary. So the change in height. What is the change in height, including the uncertainty?
67.5 minus 8.6.
Yep, exactly. Same thing as before. Yep. Okay. 58.9. So first we calculate the value itself, right, without any uncertainty. Exactly. All right. Centimeters. Okay. Then what about the uncertainty?
Plus or minus 0.2.
Okay. And why is that?
Because there's equal amount of there's 0.1 centimeter uncertainty for both the heights.
Okay, yep. So basically the plus minus delta H is 0.1. So in other words, we add them up still. So the trick is just for actually to know that for multiplication division, it's adding up as well. With the percentage, that's the main difference. Here we go just by the value. Okay, so we can say 58.9 plus minus 0.2. Huh? And okay, I mean here it's obvious, right? But in some cases it might be a bit different. So again, here it's coming automatically that we have the value of 0.9, also 1 digit, hence this one by 1 digit as well. Okay, but of course here you can't do much else. It would be more like if you would go by the percentage deviation to make sure that this is then in the end 1 digit as well. Okay, question 2C. What is the mean value of t?
Zero 0.88 plus 0.82.
Okay, exactly. Okay, and then
Divide by 4.
right. So what we can say for the mean is basically a weighted average related to the number of values we have. So there's no weight behind. So it's an unweighted average, if you want to say so, because every value has the same equal importance or weight, right? In that case, we could call it the weight actually. So if you would have 6 values, you would divide it by 6. If you would have 10 values, you would divide it by 10. Simple as that. So always the mean is always simple as that. So that's why sometimes it's not the best expression, because we just take every measurement equal and divide it. There's pros and cons for that, but in some situations it's not the best way. But here it's important to realize, well, it's just straightforward. And if I do that, I get 0.84. I mean, sometimes even if when you look at the numbers, right, you can actually kind of see it. It's 8, 2, also 0, 2, 0, 2, 6, 8. So in that regards, it must result in the 0.84 without a large, massive calculation. Okay, and what about the plus minus? This is now a bit different to what we had so far. It's very practical, actually, very simple. But at first it seems okay. But you just think straightforward, simple, and say, okay, I have 4 values, and I should calculate out of that the uncertainty. So, what is the straightforward way to do so, to calculate that uncertainty as a value?
I don't know the uncertainty for each.
Okay. Yeah, I mean, exactly. Yeah, that's a good answer. I mean, insofar that's correct. So you have to help yourself, so to speak, with a certain approximation. That's something. That's why I say this is straightforward. Actually, very simple. Not the most accurate of them all, actually, but it's at least something which helps you a bit, so to speak. And when you look at it, my values, they go from 0.8 to 0.88, huh? And well, of course, it could have been slightly different distributed values. So not necessarily is the average in 0.84. It's of course a result of the individual values. Could have been a bit more say instead of 0.86 could have been 0.87. Instead of 0.82, it could have been 0.83. So that would have shifted the average, of course, to a higher value. So just because it's so nice in between doesn't mean it's per se the average value, frankly speaking. But for the uncertainty, that comes now into play. Because now we make it very simple and say, well, the delta is actually, or the range actually, which is the maximum difference between the lowest and the highest value. Insofar, that's what we take. So we take the delta t and take it by half. Of course, plus minus then. So it's a pretty roughneck approach to some degree, which means you get 0.08 and you halve it into 2, because the difference between the largest and the lowest is 0.08. And you say, well, in the middle of that, without considering the real distribution of the values, I get the uncertainty. So if you would really want to be precise, you would have to go into the statistics with the sigma in order to calculate it with the true deviation. But of course, not with 4 values. That would be too low. You would have to start at least 5 to 10 values in order to get a good, reliable sigma, so to speak, also the deviation from the average. But this is an approximation of a value, hence, of course, we get 0.04. Huh? And by coincidence, in this context, both have the same digit range. Huh? Okay, so far, Chris, with that one?
Yeah.
No? So, I mean, I would only say, just what can you say about, forget about the precision, but what about the accuracy? Well, can we say something about the accuracy?
Yeah, I think so, because we have the uncertainty.
Okay, yeah, all right. It's a good point. You know, this one is nearly going a bit more into the statistics, but already on a bit more sophisticated level. Also, the numbers are very simple, and of course, what we do here is quite simple in terms of how we calculated it. But the point is, we don't really, strictly speaking, we don't really know the accuracy of the data because we don't know how true the readings are to the true value. Right? When you look at it, we don't see anything related to the value actually, or the so-called true value. And we would need that in order to say it can be accurate or not. So it's a bit a trick question to some degree, because what we talk about here is something about unknown, meaning the true value is an unknown. And as the true value is unknown, we cannot really talk about the accuracy. Huh? Would you agree with that?
Yeah.
Okay, yeah, right. So it's important because we have on one side pretty, it's an approximation here, again, as we said, it is 0.04. We have the values here, 2 more, but for all of them, we don't really know how close the whole thing is actually to the true value. Is it 90? Is it 78 or what? So that's why, and of course it depends. In this context, it's the cylinder rolling down, and then we measure the time. So it's of course 0.88 seconds. That seems to be, even if that one now looks, well, 0.8 to 0.88, but it's within 100, also 800ths of a second, right? So that seems to be, for that purpose, quite okay. If you would go into particle physics, that would be completely useless, of course. But it's always a matter of what are we talking about, huh? in what context is it to be seen. And what about that question h1? If we would reduce the value of h1, if we make that a bit less high, or reduce the height a bit of the starting point, first of all, what kind of effect does that have? If I make it, let's say, up to here, then my line goes like that, or like better like this. What effect does that have on the experiment in regards to what you measure?
The height would change, but the uncertainty value will not change.
Ah, okay. When you think of it, okay, of course, if you go with your measurement with the camera, then I fully agree with you. If you go by a standard method of just stopwatch, then will the cylinder roll down at the same speed, or will it be less fast or slower?
I think less fast.
Yeah, exactly right. So it's of course it's only possible because of the influence of the same gravitational field, right? That's why we can say what we just said, and you're correct. So it will roll down slower. That means the passing, also the speed is obviously less. That means the passing of a certain point happens with a slower, within a longer time, kind of, or not so fast as we usually say. That means I can basically be more accurate with my manual stopwatch when it passes that finishing line, because my let's say eye movement, or my eyes are comparatively slow. Right. Some animals can actually measure that much faster. That's why they can catch a fly, for example, a frog. We can't. Luckily, we are not a frog, so to speak. But then, of course, that's why we see that in a different speed, so to say. Or a frog may see something like what we would perceive as a slow motion. They see that on a regular basis, so they can see the flapping of the wings and stuff like that. Hence, they can actually shoot out and catch the fly. We can't. I mean, just from the eye, I mean now. So that means if that now rolls slower, that comes closer to what we can measure with our, let's say, the laxness of our eyes, or the slowness of our eyes. It's like the resolution a bit, but this time in time, movement over distance over time. So henceforth, we have a better accuracy, and that will henceforth reduce the uncertainty, right? Because in tendency, when we make now 5 or 4 measurements, like in this case, then we can expect that it will come closer to each value to the other, and henceforth the uncertainty will be less. So the reaction time is a bit different. That's basically what it's all about in this one, huh? Okay, let me just see. So how about the next one? So we have to get to calculate the relationship between time and acceleration of free fall. So there's a couple of parameters included here. So still about the same. So we link the height, the distance on the ramp, of course the influence of the G, we know that. And now we want to go the other way around and say, okay, what is the uncertainty for the value of G? If we use that experiment, we can obviously measure everything but G. So, or in other words, what it says here, the relationship between T and the acceleration. So what do we have to do in order to get an answer? in A. So in 2, excuse me. Of course we have to, but what do we have to do, Chris? What is expected in order to get some feasible answer? So you have to calculate. You have to calculate the uncertainty of G. Forget about this one right now. Actually, of course, it's part of the answer, but so the uncertainty of G. So when you look at this one, where is G, right? So G is somewhere in the formula. So what do I have to do therefore in order to get a feasible answer with what I have here given in order to talk about G?
If T, S, and H.
Okay, yeah. So what do you mean in particular, Chris? Or precisely?
We know the. Wait.
Yeah.
What is S?
This one, also the ramp, the length of the ramp.
Oh.
So the other values we already had that in our table, right? We had T, we had delta H. So, or in other words, in the previous parts, we already calculated the respective values, right? So we have this one with the uncertainty, we have this one with the uncertainty, and the S is now given, so we don't have to calculate it, it's just a given. And now the question is, how about the uncertainty for G? So what is my first step in order to get the uncertainty of G? Or before I even can calculate the uncertainty, what do I have to calculate first?
Uncertainty of the other ones.
Those you have, we calculated that, right? You see, right? We calculated them already. Here, and it's a given with the S. That was a given. So just, it's a bit complicated, right? What I want to drive home the message is, even if it's complicated, when we had to calculate the delta H uncertainty, what do we do first? Or the one with the velocity before, sorry about this one. So here, right, in this question, what did we calculate first when you look at this one? Before we went into the uncertainty, what do we always first calculate?
Percentage.
Before that, you're right, but before that, when you look at this question A, what have we calculated here, Chris?
Oh, the original, the total value.
Yeah, exactly. And just the value, straightforward, without any uncertainty, whatever. Here we have a formula based upon the measurement in order to calculate V. Now, this one is just basically the same question, but just a bit more complicated the way it's asked. So we have a formula here, but does the formula show how G is calculated already or not? Just this formula, does it calculate G or not?
If we have all the values, then yes.
Okay, yeah, I know what you mean. Yes, that's a good answer. So my answer is, for what you said, However, we have to rearrange the formula. I mean, it's very straightforward, ultimately, right? I mean, right? Yes, we can calculate, but the formula here itself is not yet the one to calculate G. So what we have to do is we have to rearrange. That's the point, right? So we have to rearrange the formula. So in order to, sorry, that's the wrong way to go. So we basically can just go by 4s squared divided by t delta h. Huh? So we just have to rearrange. That's the point. And most likely in quite some question, you will probably exactly encounter the same situation. You will have to say, okay, now we have some values. This is how it's linked, how the time is linked to the height and the distance. All right, okay. And these are the values which have been measured. Like this, but then a bit differently shown like that. So you have to come up on your own with how you do it. So you see everything is a bit different here just to get the base values, or it's just given. But maybe the question is just calculate the uncertainty of G and not without question 2b and 2c, just given values like that, given values like this, and give a value like that. And then you get that formula. Now it's being said, okay, calculate G. So what you have to do is to say, okay, if I want to have the value for G, I have to rearrange first of all, because my interest is not in those. It's just what I measured. For whatever reason, to make life a bit more difficult, the formula is shown as how time and these other parameters link together. But I'm not interested in that in terms of calculating G or saying something about G. What is the uncertainty for G? So hence I have to rearrange it. That's kind of obvious, not obvious, like what we discussed now. And then we see, okay, now that's how I have to calculate G. And then, of course, I have delta H, delta A square, and T square. So what I have to do is obviously then go into the values I'm given and then just say, well, first of all, I have to calculate delta H. I have to calculate the average for the time. Okay, so I have delta H, I have T, and S is given. So step 1 or step 0 in this context was to rearrange the formula, or let's call it 1 with this. Step 2 is then get the values, meaning basically the average values, if you want to say so. And then just out of that, you have S, you have T, you have delta H. Out of that, you get G, right? Just normal procedure. So here they did it step by step, right? So this is now going for the hard level without getting it step by step. So you get the G value as a result of the rearrangement and the calculation of ST and delta H. And you calculate it like according to what we have there. And we get actually 10.014. And when you look at it, we had, so, or what is, how do I have to adjust my G value now, Chris? When you look at the various, at the values, right? You have 100.2, we had 58.9, and we had 0.84. So how do I reduce my value, or how do I adjust my value eventually? What is the value I should list?
We add the uncertainty.
Okay, all right. Exactly, right? So now it comes, of course, now it becomes a bit, all right, so how do we calculate that? So the uncertainty, now we go into the percentage, right? So we go, sorry, we go over basically delta G over G, huh? Oops. So what do we have to, when you look, now we have the formula, right? So what we can say is, of course, I mean, this is now a bit what we have not looked at before, but that's why I want to show it to you. So basically what we can say, our delta S over S, we have our delta H over H, and we have our delta T over T. Huh? And because they are, of course, either multiplication or division, so we always add them up, all three of them. And do we have to take something else in consideration, which is not yet here? When you look at the formula, yeah, 2, huh? Okay, yep. 2 and 2, huh? Twice here, twice there, exactly. Huh? So you see, it's a we already know that all. It's just seemingly more complicated, but the core is still the same. Yes, we had to rearrange the formula because we're talking about G, we are not talking about T. So of course, G as a function of S, T, and H, if you want to say so. And the function is values or parameters, better said, linked by multiplication or inverse multiplication, meaning division, right? We could as well put that one into a minus and multiply it as well as a power of -1. Okay, so we get this one. So that means, of course, now what we do is nothing else but plug in the values, and then we get the percentage. And if you do so, I'm not writing it down because I want to save a bit of time. That will result in 10.059%. So we can as well say 10%. That's fine as well. Huh? So we have the percentage uncertainty, right?
Yeah.
And now, of course, same thing. Now the question is whether it's accurate or not. So what do we have to do in order to determine, to say it's accurate or not accurate?
I think we first find the uncertainty value of G.
Yeah, okay.
1.
Yeah, okay, yep. So delta G is 0.01, yep. Oh, 0.1, excuse me. And what is there for the lower limit and what is the upper limit?
9 and 11.
I should write it like that. Sorry, my mistake. Yeah. Okay, yep. So we go by 9 and 11. Huh? Okay, so is it accurate now or not? Do we know the true value of G?
Yeah.
Okay, that is how much?
9.81.
Okay, yep. So that's important. We just know it, right? And now Ainsworth, is it now accurate or not?
Yeah.
Okay, why?
Because the real value is within the range of the the calculated value.
Exactly. Yeah. Very good. So you see, it's this is still a bit step by step. It may be that the question itself is just basically asking you this, right? Then everything else you have to figure out on your own, step by step, in order to come to that answer. Of course, we are here. It's still, again, I just repeat myself, step by step. The key point is you always repeat the same steps. That's important, right? First, you get the value. That may be the result of a formula which you still have to rearrange, like what we had encountered here. Then you just calculate the value. Standard procedure, always the same. Just take the values. You have to get the values. Well, eventually you have to figure it out yourself first. Like here, it's just H1 and H2. So obviously you have to calculate delta H on your own. Same as figuring out value for the T. It's not given. It's just the measurement values, but in a different way compared to values of height 1 and height 2. So you just have to eventually make some sub-calculations to get these values accordingly. For, in this case, S is a given. The other ones you have to calculate, delta H and T. So that was the sub-step. But in its core, it's the same, right? You just have to apply the values without the uncertainty, and then you get the value. Then, as always, you calculate the percentage, which is, of course, in this case, multiplication. Pay attention to the power and add them up accordingly, so you get the percentage. And then out of that, plus minus, you get the range. And then you can calculate it, compare it to the real value, which in very few cases, but this here is G, is expected that we know that. So in other cases we don't know, but when it comes to this, let's call it kind of constant in certain situations, at least like G on planet Earth, as an accepted average value, then yes, we can compare it. Huh? Okay, all right. For next time, Chris, of course we can continue with that, but what other subject would you like to cover? But I think we don't have any lesson next Friday, right? As far as I see.
Wait.
No, we did. Sorry, my bad. No, we have lesson. Okay. All right, just to make sure. So, what would you like to cover next time?
Let me check what I'm learning.
Mm-hmm. Yeah.
Oh, right now we're learning the kinetic energy, like between the gravitational potential energy and kinetic energy.
Okay, so we should still look into that. Is that okay?
I think we already did it.
Yeah, we did some, exactly. So that's why I'm asking. Of course, there's always more questions, no problem with that. But it's just a matter of, do you think it's helpful or not, right? Or what else would you rather do?
Because right now in class we're doing we're simulating I think it's paper 3, we're doing the practical paper.
Ah, okay. There's probably not so much to be done by us here in tutoring in tendency. Let me think. Well, what we could do is, okay, so if it's okay for you, Chris, I will check some past papers. Maybe, then we can maybe look into some of the past papers of how it works. Huh? Is that okay?
Yeah, but I'm thinking maybe we could just continue to other the new topics.
Okay, fine. So if I look at this, I'm just straightforward on the sequence. Basically, well, well, we could go into matter and material, so meaning density, pressure, stretching, elastic potential energy. That would be one topic, or electric current is another one. With resistance, let me see, resistance and resistive practicals. Well, practical circuits we can do as well at some point, but maybe not yet. I think it's still good to cover. So, well, yeah, I would suggest either we do talk about or investigate, solve questions about density, pressure, or we go into electric currents, which is more the typical. What do you think, Chris?
I think the pressure and density.
Okay, all right, okay, good. Then you go for chapter 7. Okay, density, pressure, okay. All right, okay. Then we deal with that, huh? Okay. As I said, I will still send you that solution. Would you like to have the open questions, which we have not done? There are a couple of questions more. Would you like to have them sent to you?
Yeah.
I'll send it then. Okay. And I will send them. There's quite some actually, but it repeats itself. It's good for you to practice, but not necessarily so helpful to do more in tutoring actually, huh? And if there's a question, of course, we can always discuss it. All right. Okay. Good. Then thank you, Chris. Have a good weekend and week, and see you next Friday, huh?
Yeah. All right. See you.
All right. See you then. Thank you.
Wow. Reconstruct your mobile phone.